Okay, we've talked about so far in this unit the use of significant digits and rulers and the uncertainty digits and that sort of thing. And so I'm going to create a line here, and we're going to measure it just to give us something to measure. I'm going to throw it on there, and it looks like it is. I'll put it on the end. I can't get to the 0 because it's all the way at the end, but you guys are smart enough to figure this part out. All right. Oh, wow. Okay. All right, so according to my approximation, this looks like it is 1, 2.32 centimeters, right? That you guys, are we okay with that? How I got that, right? Okay, so the 2 and the 3, everybody should be getting to the 2 and the 3 because it's marked right there on the line. We have an actual delineated mark for that, and then we get our uncertainty digit after that. Yes? Okay, that's what the significant digits PDawg taught us there. Okay, now, what if, and just for argument's sake, we have a line that is nice. Did I get it? Start at the 0. Okay. What if we have a line like that? This looks to me to be 2.00 centimeters, right? You guys follow me? So we go right to, you want to be taking notes on this. Why your composition book isn't open, I don't understand. Okay. 2 centimeters. Okay. And then right there, I don't see that going past, okay, to my eye. Therefore, the uncertainty digit that I'm adding to it is another 0 because it's not a little past, it's not a little before. I think it's right on the line. Okay. So we have created this number with that being our uncertainty digit, right?
Yes.
You guys, we're good there. Yeah, that's where we've been so far. Okay. Problem is, well, this could also be written as 20 millimeters. Yeah? Okay. And if there was a unit that was 1/10 of a mil, there isn't a unit that's 1/10 of a millimeter. It goes down to a okay. The next unit down from millimeter is called a micrometer. Okay, it's got this funny little U on it, and it is 1,000 of these equals 1 millimeter. So this would wind up being 20,000 micrometers, also known as a micron. That's the other name for it. You may have heard of that. Problem is, how many units of digits of precision did I have when I first measured this? I was able to get down to we had 3 digits, right? The 2 and this 0 and then this 0. That's how many units of precision we had. Okay. How do I communicate that 0 right there, this 0, is the precision of our measurement? Where? Where can I put a decimal, preserve the fact that this is 20,000 microns, but still express that that's the measure of our precision, right? We have a method for that. We have an actual method for that, and we'll get to that in a minute. Okay, and that's kind of the cumulative thing that we're going to do with today's lecture. Okay, so how do we? So that's the question that we're going to be answering today, and the process we go with it. How do we measure our precision if we have too many zeros. Because that's what's going on here. We have too many zeros right here. We stopped somewhere in the middle of them for the precision of our measurement. All right, and this happens sometimes. Okay, so how do we account for this? We have three rules that account, well, four rules, but one of them is kind of implied. Okay, so we'll call it the zeroth rule. Rule 0. Which is funny because it refers to non-zero digits, so it's the zeroth rule, right? That's irony. Okay. Okay. All non-zero digits are significant. That is our first rule. So if we have a number, let's say 3, 1, 2. 312 has 3 significant digits. Pretty straightforward, right? 312 or 3.12 or 31.2, for example, would have 3 significant digits. Yeah, that's a pretty obvious one. Okay, rule 1. Rule 1. Okay, that's rule number 1. All zeros in between non-zero digits are always significant. So our example here is going to be 1003. The fact that we wrote a 3 here, that our last place that we have a value, okay, has a non-zero digit, means that everything in between there, between this one and that one, is also significant. Yeah, this is distinguishing between 1004 and 1002. Yeah? All right, so we know that it's that those zeros matter as far as the precision of our measurement. So this would have how many? This would have 4 significant digits. Yeah? Okay. Rule number 3. 2. That's what I said. 2. 1, 2, 5. 3, 3. If you haven't seen the movie, you wouldn't get it. Okay. Number 2 is, I want to make sure I'm wording this right. All zeros to the left of the first non-zero digit are never significant. Okay, so here's my example. We discovered that this was 20 millimeters, right? 20.0 millimeters. If I were to measure this in kilometers, we still know that this many millimeters, but the decimal is going to fly way out to the left, and it's going to be 0.0000200 kilometers. These, oh no, wait, nope. Count the 2, sorry. These don't matter. Leading zeros are never significant. All they do is show you that the value of what you're dealing with is small. It doesn't tell you the precision of your measurement. All right? Okay. Now, rule number 3. Yeah. 0, 1, 2, and 3. I wrote the 0, 1 because it was just kind of, it's kind of obvious. Okay, number 3. Zeros to the right of the last non-zero digit are only significant in the presence of a decimal. Okay, so what we have here, we have 4 rules. First one, all non-zeros are significant. Okay. Then we have always, sometimes, always, never, and sometimes. Enough. Okay, so we have always, never, and this is sometimes. All right, and here is our example. Okay, we have this bad boy right here, this 20,000 micrometers. If I just wrote the number 20,000, if I just wrote the number 20,000, you cannot tell by looking at this where our digit of uncertainty is. Or you can, and it's forced to be that one. It has to be the first non-zero digit. We only get one. This has one significant digit. Now, if I put a decimal in there, what is the value of this number? How much is it? 2,000, right? 2,000. But we know it's precise to what digit? Stay with us. Stay with us. Okay, we know it's precise to which place? That 10,000th place, right? That's why we have that zero. I'm sorry, the 10th place. Not 10,000th place. The 10th place. Okay, but that decimal is there telling us that that last number, that we measured 2,000 all the way down to the 10th place. That means this number has 5 significant digits. In the presence of a decimal, all zeros to the left, all zeros to the right count. So, how many sig figs are in this number? Okay, 206,000. We have a tweener that counts. We have trailers, they don't. Why don't they? And there's no decimal. Okay. Three significant digits. I see you, Chris. Just so. Okay. How about that one? Leaders, ones to the left, never count, right? Rule number 1. I'm sorry, rule number 2. Tweeners do count, always count, right? Okay, so that one does count. Does this one count? Is there a decimal? So it's to the right. It's a sometimes. Is there a decimal in the number? Way over here. Yes. Even though it's way the heck over here, this decimal makes that one count. Okay. All right. So this is going to have how many? Nope. These don't count. They matter. They're not significant. They matter for the size of the number. They still have to be there to show that this number is that small. But they're not significant when it comes to the precision of our measurement. Those matter for the precision of our measurement. So there would be 4 the old school way of calling them are significant figures. So I have a habit of calling them SF, not SD. Significant digits. All right. Which brings us back to our question. Our question was, how do we account if we measured this to be 2.00 centimeters or 20.0 millimeters, but we need units of micrometers or microns? We know that we have 3 significant digits, 1, 2, 3, 1, 2, 3, right? And according to our rules here, trailing zeros, right? Trailing zeros, there's a decimal, all 3 of those count. Trailing decimal, trailing zeros, all 3 of those count, yeah? This is not incorrect though, this is still 20,000 micrometers. But how do I tell somebody that it's not 20,100 micrometers? Or 19,900 micrometers? What's that? Where do I put the decimal? At the end? Well, if I do this, and I put a decimal at the end, that means I get 20 decimal right there, right? Now how many significant digits do we have? How many did I have here? I wasn't that precise, was I? My measurement wasn't five digits precise. So that, good guess. Are we going to need a decimal? Yes, we will need a decimal at some point. Where does it go? Chris, I'm sorry, what was your question before? Okay. After the second zero. Okay, so we do, what value is that? Oh. Okay, so we do it after the first zero. Now what's our value? 20. We need to keep our 20,000, right? So how do we show this number to be 20,000 and get a decimal in there without affecting the size of the number? Nick? Well, if we add more zeros, that means we're adding more precision to our measurement, right? And we can't lie about that. We only have 3 digits of precision. Yeah?
Yeah. You put it in front of the 2?
In front of the 2. So if we put it in front of the 2, it's going to be 0. We put a 0 there because it doesn't matter, right? Still 5 sig figs, and our value is now 2/10, and we need 20,000. How are we going to do this? Jenny, you got it?
No,
You change your mind? Okay. We have a tool for this. You guys have even heard of this tool, but what we've just done is come up with the reason why we have this tool. You've used it before. You probably complained to your teacher, why do we do this? There's no reason for this. Here's the reason. The tool we have is called scientific notation. This is why we have scientific notation. Because watch, we're going to write down all of our how many significant digits do we have in this number right here? It's the same as this, same as that, but this is our problem. We have 3 of them, right? It's the 2, the 0, and the 0. Those are our significant digits. We know that those numbers we are precise to. But how do we show that it's still 20,000 big? Well, here's how we do it. These 0, we're going to need a decimal, right? Because we have to make those zeros count. The decimal goes behind the first non-zero digit. Yeah? So now this has all 3 significant digits, right? But now we're going to multiply this by a power of 10 to show that it's 20,000. If we're putting the decimal here, then we need to go from here, here to there, right? How many places is that? 4 places, not negative 4. We want this number to get bigger, right? So this would be 10 to the 4th. And all of a sudden, we have this number, this value has the right number of sig figs, and it's the right size. This is why we do scientific notation. Mind blown?
Yeah.
Okay. Good. I'm glad. I'm glad to see the cranial carnage all over the room. Okay. Where was I? Okay, so, new situation. We have our pale blue dot that we live on. You guys ever noticed how those aren't really 2 people talking? That's supposed to be. What's that?
That's the Earth.
Yeah. Our pale blue dot. All right. I'll use this because I don't really have a yellow that works. Okay, here's our sun. The distance from the Earth to the sun is 93 million miles. However, what if I told you that we actually know this distance to the nearest thousandth of a mile? Okay, we don't. And we can calculate the average, and we've calculated the average, and we actually know it to well more than that, but there's numbers all along the way. Okay, so what if it just happened to be 93 million right on the nose all the way down to this thousands place, to this place right here? How would we write this number? How would we express 93 million to a scientific colleague maintaining the number of, maintaining how many digits of precision do we have? 5, right? Right, so if we go down to this place, then that counts, and that counts, and that counts, and that counts, and that counts, right?
Is there a decimal record?
Not yet. Where would you put the decimal in order to make those 5 count? Show that those 5 count.
After the 3 zeros?
Do it. Do it. So in other words, how would you write this number in scientific notation showing that we're good to that decimal spot? How would you write that? Okay. Anyone got it? Brian, you got it? Okay. How many significant digits do we have? If we know we're accurate to this digit, how many do we have? 1, 2, 3, 4, 5, right?
Yes.
Okay. So what do? We write our significant digits. Yeah?
Yes, sir.
Then what do we do with the decimal? Where do we put it?
After.
Nope. After the first non-zero digit, which is the 9. 9.3000. Now, how far do we have to move the decimal in order to show that it's really this big of a number?
A long way.
How many?
7.
Count them out.
7.
1, 2, 3, 4, 5, 6, 7. Times 10 to the 7th miles. This is how we write that number. Okay? All right.